So what I didn't quite get the concept of Hilbert space.
Right. Okay. So Hilbert space is just a fancy name for a vector space. Okay. So Hilbert space is just a fancy name for a vector space. So it's a vector space. And the space can be finite or infinite dimensional, right? You know, and the thing that it must have it with a um, with a with an inner product, with a, okay, I should say with a positive definite, with a positive definite or semi-definite, I don't know what it is. You could, হয় zero হতে পারবে অথবা positive, with a positive definite inner product. Okay. As far as I know, this is basically what a Hilbert space is. So, you know, for the finite case that we were looking at, the spin, so, you know, this was our one of our basis because our Hilbert space, our vector space was two-dimensional. This is a convenient basis. So if I take two vectors from this Hilbert space, there exists an inner product, which is simply the, you know, if this is a row vector, this is a row vector, this is a column vector. So this is just a matrix multiplication. And this is some number, a complex number, right? So now what about the positive definiteness? If you take this guy and take its inner product with itself, what you're doing is essentially you're looking at the norm squared of this vector. And positive definiteness means that this has to be greater or equal to 0. And it is 0 if and only if, like this is 0, if and only if the vector itself is 0. That is, if the vector has this form. Okay? So that's just a Hilbert space. But you can have infinite number of functions. So suppose you have like functions of x, and suppose that so here, you know, sorry, not x2. So here, for example, suppose these are you have lots of these functions. Suppose these are nice functions such that, you know, this thing exists. If you take one function from this set, another function from this set, and evaluate this integral exists, meaning that this is, you know, doesn't blow up, right? You know, meaning that if I take its mod, then this will be less than infinity, right? So in that case, you know, this set of functions, there are an infinite number of those. You can actually find a convenient basis for them, and that basis is the Fourier basis. So any function that satisfy this can be expressed as an integral over some constants, which we don't really care about at the moment, times these are the basis vectors. They are analogous to these guys. And there are an infinite number of them because k, the momentum vector, can be any real number. And then a is the coefficient of linear combination. Then d of k. So this is just saying any vector in your infinite dimensional vector space can be expressed as a linear combination of these basis vectors. And that the inner product between two vectors in this space is simply given by this thing. And this has to be, okay, this is a complex number in general, but if I say take any of these vectors and compute their norm squared, so if I take psi and do psi, then it's dx psi star psi. And this is a positive number, as you can see. And this has to be less than, this has to be convergent, of course, less than infinity. But it also has to be equal to or greater than 0, which it is by inspection, right? And because this is a positive definite quantity. And of course, because it's a positive definite quantity, it's obvious that this thing is exactly 0, if and only if the function itself is just the trivial 0 function. Okay?
Yes, sir. Sir, also you mentioned a point like if the if two vectors have the same or the different constant multiplied, they don't
Right.
generally represent two different physical states or something like
Right. That's an
that.
interpretation of the Hilbert space in terms of physics, right? I mean, I don't think the definition of a Hilbert space has anything, I mean, vectors are just very, very yeah. I'm not sure. I don't think the definition of Hilbert space has that restriction. That's just that it's when we apply to physics, what we say is that if I take a vector from my vector space that is a function, and then I take another vector in the same vector space, which is the same function but multiplied by some constant lambda, then physically they are equivalent. Okay, that's one of the postulates of quantum mechanics. Okay, this is nothing to do with, as far as I know, this has nothing to do with the definition of vector space. Okay,
Okay, sir, understood.
can psi be 1 comma I? Yes, of course. Yes. Can this be? Can psi have like be of this form? Of course it can. You just take psi and you say, okay, I'm going to take the up vector plus I times the down vector. These coefficients can be anything, any complex numbers.